Okay, so hopefully you were able to get that one figured out. Let's go through and start with our very first one. Okay, so we're going to clear up some space. Br2, we said we were referencing this as an electrophile. We take our pi electrons, we share those with our bromine, which would cause our leaving group to leave. Lone pair electrons would come back and react. Okay, lots of stuff happening there. I get sometimes people going through and say, well, there's no way that that could possibly all happen because they're too far away. Those arrows are too long. Well, to that, this is what I would show. It isn't all that far away. Okay? We've just decided to not always draw the structures as incredibly close to each other as possible because we aren't concerned about that. What we're concerned about is making sure that our arrows do what we think they should do. And as long as they do what we think we should do, we don't really care about the immediate proximity. Okay? You'll also notice that one of the problems with redrawing it as I drew down below is that these two now look next to each other, where here they were on opposite sides. Okay? If we maintain our starting drawing, it's a little bit easier to see the potential stereochemistry that comes out of this. Our bromine is connected here. It's going to have two lone pairs and a positive charge. Why positive? It has accepted electrons, lost electrons, and lost electrons again. Right? So we could argue that these two cancel out, and then this last one is what makes it formally positive. What happened to our carbon, our alkene? Well, one carbon donated electrons, right, because it stole the pi electrons. So it stole the pi and then donated, neutral. The other one lost and then gained from the bromine. So the net result is that our carbons come out neutral. Our intermediate structure, ta-da, we've got our three-membered ring. And then we also have floating around Br minus. So back when I was talking about should we move forward or not, well, let's look at this three-membered intermediate. Do we really want a positive bromine? Bromine's very electronegative. That's not very likely. So I would expect the other bromine to come in and attack. Okay? I would expect it to come in a backside fashion because the other bromine is blocking the top. The result, we would get this bromine up here and this bromine down here. Okay? We could go in and show all our lone pair electrons, and we'd say, well, ta-da, now we have a product. And if you got that, phenomenal, that is great. Okay? But of course, there's a problem with it. As soon as we've drawn a product, we should now go back and think about stereochemistry, everybody's favorite subject. And yes, both of these are stereocenters, which means we need to specify the stereochemistry, otherwise we'll likely be getting the answer wrong. For those people being like, well, what do you mean likely? Look at the question. If the question answer choices in a multiple choice don't specify stereochemistry, don't worry about it. If they do, then you need to worry about it, okay? And even then, they may be doing it just to mislead you. Okay, so don't just jump all over stereochemistry when you see it. So how do we ensure our stereochemistry is all correct? Well, for me personally, what I would try and do is envision this molecule as, simply is not the right word, but as evenly as humanly possible. Okay? And that is a bit challenging. And I can't actually show the camera with the molecule up here, but I'll make a couple descriptions and then I'll gesture it through with my hands. You'll note that the carbon backbone in each and every single one of my drawings is the same, because I'm trying to ensure that I don't lose the alignment of those groups, that I don't lose that trans characteristics. Okay? It is not trans in the product per se. We could reference it as S-trans because it's a sigma bond in between. Okay? There's the S part of that. Okay? So if we do that, then I don't have stress about it. But now I do have to worry about where the bromines are located. Okay? Are they wedged or are they dashed? Or are they one of each? For that, what I would go back and do is think about that starting material and how this reaction worked. This reaction worked because there were p orbitals coming in and out of the plane. Okay? And that reaction could have occurred where that red bromine was up at you or back away from you. I'm just going to pick one. I'm going to pick up at me. Okay? If it is up at me, it would then be wedged, which would mean wedged in my intermediates. Right? And they would both have to be wedged because I can't get a three-membered ring that is partially wedged and partially dashed, which then means the end, that red bromine, is wedged. Well, the green bromine had to come in from the backside. Right? That was part of that attack. This was a backside, kind of like an SN2. Right? In fact, it is an SN2 mechanistic step. And it's coming in from the backside of that structure because the bromine was wedged, the red bromine was wedged, the green bromine must be dashed. And there it is. Okay? Complications behind this? Of course. I said the bromine was wedged. It could have come in and formed the ring dashed. Okay? Which is going to mean both of those positions are going to alternate. Okay? Well, are those structures the same or are they different? Turns out they're enantiomers of each other. So we do get two products here. Okay? We get those enantiomers. The next fun aspect to address is in this intermediate. Was there really a difference between, let's call it the blue and the orange carbons? Right? Well, no. Does that really matter? So there we go, our blue and our orange. Does that really matter? Well, yeah, because that bromine could have attacked there, which then means, as a potential product, we could be seeing the green bromine at the other position and the red bromine over here. Oh my God, so I got four products? Maybe. Okay. What do I mean by maybe? Because if we go through and look at these, you might go, yeah, that's four products, dude. Those do not overlap. Well, sort of. They only don't overlap because I've labeled them as red and green. I can't tell a difference between the bromines, which means I really only get two products. Okay? And those two products are enantiomers of each other. Okay? If I labeled one bromine, now it becomes problematic. Okay? But really those two extra products are really just repeats of the two above. Okay? Nothing's new or unique about those. Okay? So, fast, easy question turned into 5 minutes. Right? It can be challenging. Slowly work your way through it. Okay? Why is my stuff not doing what I want it to? Okay, so do you want to take another second here to actually pause and work your way through? I'll give you that opportunity, but now we'll go through and take another swing at, say, the next one. Okay, what happens here? Well, we've got the mercury OAC. If we drew that out, and this is where people are like, but why is it not drawn out? Because we expect you to memorize some things, and we expect you to be able to draw these Lewis structures. What is AC? AC is an acetyl. Okay, will I tell you that on the exam? Yeah, I will. Okay, because I think it's dumb to make you memorize things like that. Okay, so if we go through and think about it again, do we have a good leaving group? Yes, we actually have two. Okay, but we really only need to worry about one. Our pi electrons come out, attack the mercury. We break off the acetyl. The mercury reacts back. And the result is that I would get a bond to the mercury which would then be bonding to OAC, and then I would also have this floating around, the acetyl. Okay, the acetyl in and of itself is kind of like trash, so I don't need to worry about that one. What I need to worry about is that mercury piece. Okay, there's sorry, and if we look at this, the mercury started neutral, gained electrons. Okay, so it's negative, lost electrons, became positive, lost electrons again, became positive again, and so it would be positive. So again, that charged intermediate, not particularly stable, which means I need to continue to react this. So I need to look for something to act as a nucleophile. One option would be to pull out that negative charge and be like, negative, let's have that negative go through and attack. However, that negative is involved in deep resonance, which means not a nucleophile. Well, dang, what do I have left over? This is where remembering what we have back at the beginning can help out. We have HOH with a lone pair of electrons. Okay? The concentration of the water is significantly higher than the acetyl. That concentration increases its activity and makes it to be the more likely nucleophile. This one now becomes a little bit more challenging than the last one because we have two positions that it could react. Are they the same? Well, no. Okay. One, let's call it red. Red is sterically unhindered. And the orange is sterically hindered. Okay, well, how is that going to dictate which product we get? Well, if that was the only thing we were considering, we would probably want the unhindered spot. But we also have to consider the fact that mercury does not want to be positive and is already trying to leave the structure. Because it is trying to leave the structure, it wants to leave behind the most stable carbocation. Great leaving groups. We don't care about steric hindrance. What we care about is the stability of the forming carbocation. Does a carbocation actually form? No. We'd get our mercury OAC, and then we would get our water connected with that positive charge. Does it want to be positive? No. More water can come into play with another lone pair of electrons, pick up the hydrogen, and we would end with, and for those of you wondering about that end word, we'll deal with that in a second, our OH and mercury added across the pi bond. Note the OH goes to the more substituted position. Why? The mechanism told us why. We had that incredibly unstable intermediate that is dying to bust open, okay, which means we're going to try and have that water attack the most substituted position. Okay? So that's an important piece because we'll keep seeing that pop up again. We do form that charged oxonium structure with the once the water is attacked, but water can again go through and do an acid-base reaction and stabilize that. That would be what I would expect you to get for a product. For those of you that have been doing enough reading in the textbook, you're probably like, but that's not the product the textbook shows. It's also not the reaction the textbook shows. Mercury is not a common species connected to a structure, and we very often want to get rid of it. Okay? That's metal. We don't want metal in our organic structures, so we would have to cleave that off. Do we need another reaction? Yes. That other reaction has not been specified, so we're not going to worry about it for the moment. Okay? As we continue on, we're going to continue to get kind of, well, actually, we'll just move to the bottom one, because this one's a little bit easier. Our MCPBA, you'll note, you're like, why? What is that? Okay, what MCPBA is referring to is metachloro MC peroxybenzoic acid. For those of you paying attention, there's our electrophilic species. This comes in, attacks. We break that bond. These electrons can go up and pick up the hydrogen. Okay? The lone pair on the oxygen can come back to over there. That's a lot of arrows. That's how many arrows you're supposed to be showing. And note, you're still following the same pattern we've typically done. Okay? Right there is our standard pattern. We have the alkene attack, kick off the leaving group, and then our nucleophile or our electrophilic nucleophile come back and attack again. The only thing that's different here is that we're also addressing some resonance and an acid-base reaction. Why is that acid-base reaction important? Well, if we go through and show the product on this, if we look generally where we've got this set up, oxygen connected, and then we'd have the peroxybenzoic or the metachlorobenzoic acid, and we'd have our answer. Okay? This piece is largely ignored. The big thing we care about here was that we had that electrophilic and nucleophilic oxygen. The rest was just kind of trash. Okay? The big thing that comes in at the end is that that oxygen is neutral, which means no need to continue. We can stop at that structure. That structure is known as an epoxide, and that is a very common functional group that we'll look at again in depth a little bit later this semester. Right? I know we're running out of time. The other piece, this is 2 electrophilic sites. Sorry, not electrophilic, chiral atoms. So we do have to worry about chirality here. But again, note how I'm drawing that carbon backbone. I'm trying to not adjust it. We can draw these as both wedge, and we could have drawn them as dash. Does that result in 2 products? Good question for you to answer. Last one is extra nasty. So I'm just going to try and walk through this one because you've been exceptionally patient so far. So let's try and go through this one a little bit faster. These 2 species, strong base and that acid, we should be triggering that reaction needs to happen first because we know the alkene is a nucleophile. If it's a nucleophile, it's not going to react with the base, which means sodium hydroxide needs to react with our chloroform, and what will happen is the hydroxide can remove a hydrogen. The result is we'd get that negative carbon. Okay? You might say, is that hydrogen really all that acidic? Well, 3 chlorines. Chlorines are very electronegative, so yeah, that hydrogen is decently acidic. Okay? The next part, is chlorine a decent leaving group? Yup. And what do we end up forming? Our fun special carbene, similar to our diazomethane, okay, which can act as both an electrophile because of the empty p orbital, and as a nucleophile, our electrons can come in and back out. The resulting structure, chlorine, whoops, not chlorine, carbon bonded with 2 chlorines, and then we'd have that wedged. Okay, this is a fun question that I want you to now go through and address because we have 3 stereocenters, and this is a complex enough question that I'm going to suggest you look at it on Piazza and tell me how many products you get and what would the relationship be between said products. With that, thank you for your patience and listening.